Since section 1.7 is a rather pivotal, no pun intended, section, I thought it'd be worth looking at some of the homework. So I'm going to go through the evens. You have the odds. If you want to tackle the homework first and then come back and look at this video if you need help, that's great. I'm going to try to keep it pretty spoiler free, so you could watch this safely first without ruining the joy of discovery. Okay, so let's take a look at number 2. For 1 through 4, it says determine if the vectors are linearly independent. So the basic idea would be to say I need, an extra 0, 0, 0 on the end, and then you'll do RREF on this 3 by 4 matrix, and you will see if there's a free variable, and if there is, then there's more than the trivial solution, and it's dependent. You can certainly do exactly the same thing on number 4. Looking at number 4, since there's only 2 vectors, the only way for them to be dependent is if one's a multiple of the other. And it doesn't quite work on number 4. I would need to, for the bottom entries to match, I'd have to do like -3 of the first vector. But -3 of the first vector for the top entry produces positive 3. So if this was +3, -9, these 2 vectors would be dependent because the first one would be -3 times the first one to make the second one. Without that happening, it looks to me like they're independent. But again, you can actually row reduce the 2 by 3 to get there. For 5 through 8, they say determine if the columns of the matrix form a linearly independent set. So really it's the same question. They just wrote it in a matrix instead of separate vectors for some reason. I think my cats are trying to kill each other. I know, it gets linear algebra, pretty thrilling stuff. Blood runs hot. Anyway, the basic idea is you just look at these as, if it's more comfortable, look at these as three separate vectors, and again here you're probably going to have to do the RREF thing. On 8, same idea, but 8's where our superpower can come into play. These are 3-dimensional vectors, 3 entries, and there's 4 of them. In 3 dimensions, as soon as I can move in 3 different directions, that's as much independence as you can get. You don't need a 4th direction. There isn't a 4th direction. So these are automatically dependent. Okay, moving on to 9 and 10. It's a 2-part question. A says, for what values of h is the third vector in the span of v1 and v2? So that means some combination of v1 plus some combination of v2 equals v3. And B says for what values of h is the whole set linearly dependent, which isn't necessarily the same question. Matter of fact, looking at 10, I can see just by inspection that -3 times the first one equals the second one. So that's already a dependent set. It doesn't matter what's going on in V3. There's dependence between V1 and V2. So at least for part B, the answer to 10 is any value of h, all values of h. This will be a linearly dependent set. However, that does not necessarily mean that I can get to V3 by combining V1 and V2 somehow. So that's a little bit more of a question for row reduction. Although if you're really clever about what's going on in V1 and V2, you might be able to answer part A without doing row reduction as well. But row reduction will get you there. Okay, so let's look at the next few questions. It says determine the values of h for which the vectors are linearly dependent. So 12, 14, both of them have an h in them. You're pretty much going to have to do, unless you see something obvious, like one vector being a multiple of another, you're pretty much going to have to do row reduction and figure out what values of h would make these dependent or independent. 15 through 20, they say determine by inspection whether the vectors are linearly independent. By inspection is a mathematician's code word for just look at it. So you shouldn't have to do any work. So by inspection is your favorite phrase from now on in math classes. Hopefully you will just be able to look at these and say, yes, they're dependent, or no, they're independent. So determine whether the vectors are linearly independent. So for 16, there's only two vectors. Really, the only way for them to be dependent is if one's a multiple of the other. So let's see if that's the case. To multiply the first one by something and get the second one, it would have to be -3/2. So -3/2 times 2 makes -3. Let's check the others. -3/2 times -4 would make +12/2 or 6, and the last one, -3/2 times 8, does indeed make -12. There's linear dependence. -3/2 times the first vector equals the second vector. Got it. For 18, two-dimensional vectors, there's 4 of them, automatically dependent. And for 20, it's 3 vectors in 3 dimensions, so not automatically dependent there, but the 0 vector is present. So there's automatic dependence. I can say 0 of that vector plus 0 of that vector equals that vector, and that's dependence. Okay, 21 is the true-false, and I'm not going to walk you through that one. You are not that lucky. But I think you should be fully ready to tackle the homework now, so go to it.